Thank you for the kind introduction and welcome to my talk. So I am Bijaya Bikram Samal, from a Ph.D. research scholar from Indian Institute of Technology, Kharagpur, India. And today I'll be speaking on the controlled shape-changing components using 4D printing technology. So today I'll discuss about some of the application landscape of 4D printing technology. I will discuss about the shape memory properties, some of the programming strategies, and the two case studies which are based on the two types of 4D printing. And at the end, I'll show some of the working prototypes. So coming to the introduction, first of all, we must know what 4D printing exactly means. So 4D printing is a process to manufacture a part using a smart material. And once the part is fabricated, we can provide some external stimulus to it so that it can change its shape and size. So if we look at the broad classification of 4D printing, then it can be classified into three. So first one is the embedding of smart material during printing. Second one is the printing of single smart material, its blend or composite. And the third one is the printing of multiple smart materials altogether. So the process of 4D printing starts with selection of the right smart material as per our application areas. Then once that is done, we can choose the energy source depending upon the smart material that we have chosen. So generally here we use some of the passive energy sources like heat, pressure, gravity, etc. And once that is done, then also we have to see design for 4D printing, where we do the precise positioning or arrangement of the smart material in a certain angle or position. So if we look at the application landscape, then we can know that there is a lot of applications in all the areas of science, engineering, and technology throughout. And if we can see towards the electronics and power, then we can have smart optical switches, smart solar panels, adaptable sensors. In healthcare and industry, we can have patient-specific stents, smart valves, adaptable tire compounds, etc. And in consumer side, we can have self-assembled furniture, self-assembled fashion wares, and many more. So coming to the first case study, which was part of my MTech thesis. So it was the 4D printing by embedding of the shape memory alloy. So here it is the complete, just a minute, I'll just turn on my pointer. So this is the overview of the complete process. So you can see the process starts with the 3D CAD model. And once the CAD model has been designed, then we can go for the preparation of the material. So this preparation of the material, here we are, for our experimentation, we are using a shape memory alloy. So for preparation, we can use cutting, drilling, milling, all kind of micro machining processes. For our experimentation, we have used a wire cut EDM to cut the nickel titanium shape memory alloy that we have used. And then for drilling, we have used a laser micro machining and electrochemical micro machining. So once this preparation of the material is done, then we can go for the programming of the material. Now this is a general programming procedure for a shape memory alloy and nickel titanium. So first of all, we have to bend the part, then we have to fix it in a fixture, then we have to heat it, and then rapid quenching. And once it has remembered its shape, then we can bend it as per our own choice. And then we can go for the next step, which is the embedding of the nickel titanium shape memory alloy onto the 3D printing part. So that process starts with the 3D printing of the base. Then after that, we have to pause the printer, then embed the sheet using some pins or epoxy. Then after that, we have to resume the printer. So after that, we are left with the 4D printed part, which can go for the testing. So here we have used the nickel titanium alloy from our vendor, and once we have got it, we have done an electrodispersive spectroscopy to find out the exact composition of nickel and titanium. So here we have found out that the nickel percentage was 43% and the titanium was 56%, which is a titanium rich nickel titanium alloy, which is generally used for biomedical applications. So here, this is the design for 4D printing. So design of 4D printing is very important. So we have to first know what will be the shape after morphing so that we can provide the design parameters before the process. So here we have considered two prototypes. The first one is a 3D model of an origami, and the second one is a 3-jaw gripper. So here we can see that for the origami structure, we have provided some chamfer and gap so that we want our intended part after morphing to be perfectly meshing and 90°. So that is the reason we have considered these design parameters. Similarly, we have also considered some design parameters for 3-jaw gripper so that we want it to grab something when it goes inside the hot water. So this is the complete process of the programming of the active component. So here the active component we have considered is a nickel titanium safe memory alloy. So we want our active component to bend. So first of all, we have to bend it. Then we can fix it using any fixture or any kind of pliers. Then after that, on that position only, we have to heat it above the transition temperature of the material. And after that, we have to rapid quench it in the room temperature water. And once this process is completed, it has now remembered its shape that it has to bend when we are providing a triggering temperature to it. So this is the complete process of the 4D printing by embedding the safe memory alloy during the printing. So here for my work for the active material I had chosen nickel titanium safe memory alloy. So the passive material I had chosen a polymer, thermoplastic polymer using the FDM 3D printing. We have used Ultimaker 3. And the process starts with first 3D printing of the base, and once the base is printed, we can manually put the safe memory alloy onto it, and then we can have some fixing using some pins or epoxy resin. And this manual putting of the safe memory alloy can also be done by using some robotic arm and automation. And once it is completed, then we will resume the printer and we'll print on top of that. And once it is completed, we are left with the 4D printed part. So this is the first type of 4D printing what I am talking about. So once it is completed, we can go for the hot water actuation test. Here we can see once we have printed the part, we can use it for actuation, and it took about 22 seconds to come to its final shape. So that is a 4D printed origami structure, we can say. And for the second prototype that we have printed is a robotic gripper. Here we can see it is gripping something, and but here we have got some of the failed attempts, like there was a problem between the interface of the metal and the polymer, and so we have to design our part such that these kind of failures doesn't happen. And we can this shows the basic capability of the first kind of 4D printing technology that I'm speaking about. So this is the thing. I would like to acknowledge my professor and all the members of production engineering, Veer Surendra Sai, University of Technology, Burla, Sambalpur, India, for conducting this part of my work there. So this is the case study 2, which is the work presently I am doing in my PhD. So this is a 4D printing of safe memory polymer using the fused fabrication method. So first of all, before going into that, we have to know what is the mechanism of safe memory effect in any thermoresponsive safe memory polymer. So any thermoresponsive safe memory polymer have some common structural feature, like we have a safe fixing part and a safe switching part. The safe fixing part are the structural domains or net points in the SMP network that maintains the dimensional stability during deformation. And the safe switching parts are the long polymeric chain between the safe fixing part that are stretched during the deformation. And these safe switching parts generally store the elastic energy and are responsible for the safe recoiling of the polymer network. So here we have two parameters that we need to see, that is the safe fixation ratio and safe recovery. So these two defines the safe memory property of any thermoresponsive safe memory polymer. So the safe fixation is the ability of the material to get fixed at a certain position and angle, and safe recovery is the ability to recover back the temporary shape after it has been fixed. So here we have two programming concepts. So these concepts are based on a few things that I would like to discuss. Like first one is the programming after printing and programming during printing. So this programming after printing is a general programming procedure for many kinds of thermoresponsive safe memory materials. Like just now I had shown for the nickel titanium safe memory alloy. So we have the part, then we have to fix it in a fixture, then we have to heat it above the glass transition temperature, then after that we have to cool it. So this programming, this is the programming cycle for any kind of safe memory material. We have to do it separately. But the beauty of the FDM 3D printing process is such that this process is getting done automatically during the process. So here we can see that we have the as printed part and we are fixing it with using some fixture. But here we have the built platform onto which the hot polymeric material is getting deposited on top of this, and it is also controlled by the G code. So this fixing part is getting done automatically here during the FDM 3D printing process. And this heating above the TG is also getting done here automatically, because we have a heater here and through which the polymer material gets into, and the hot polymeric material gets deposited on top of the build platform. So these two are getting done here. And once it is completed, the nozzle goes up by depositing various layers of the material. It also gets cooled from below. So this cooling or quenching part is also getting done here automatically during the process. So that is the motivation why I am using the fused filament fabrication for processing of the safe memory polymer. And once this is completed, this programming part is completed, we can go for the recovery cycle, where we can deform it to some temporary shape, we can heat it, and then we have the recovered shape. So this is the complete process of the second case study, that is the 4D printing of safe memory polymer using FDM. So here we have to start with again the first that is the CAD model with some design specification as per the 4D printed part. So here also we have kept some chamfer and gap, so that we want our part to be perfectly 90° after the actuation. Once that is done, we have to slice it using the simplified 3D software, and once that is done, we can go for the any open source low cost DIY FDM 3D printer, and we can print it. Here for our experimentation, we have varied few parameters like printing speed and extruder temperature. We have varied the printing speed from 5 to 95 and extruder temperature from 180 to 270°, and the other parameters remaining constant. And once we have printed the part, we have the final part which we can take for the testing. So here for the characterization, I am using a fold deployable test. Here we have an in-house built setup where we have a PID controller to control the temperature of the water, and we have other stuffs here so that we can measure the angle precisely to find out the safe fixation ratio, safe recovery ratio, and safe memory index also. So here we have compared between the two programming strategies experimentally, that is the reprogramming after printing and the programming during printing that I have just now explained. So this is the angle measurement schema that we have prepared for the reprogramming after printing, and this is the programming during printing part. So these are the results that I have got. So we can see that with an increase in the speed, extruder speed, there is an increase in the recovery ratio, and with an increase in the extruder temperature, there is a decrease in the recovery ratio. Similarly, we can see that here the safe fixation is very good, that is more than 99%, but with an increase in speed, it is decreasing a bit, but it is not much prevalent. So here for the extruder temperature also, we can see that with an increasing in the extruder temperature, we are getting good fixation, but here overall the fixation ratio is very good. We can look into the recovery ratio. From the diagram also, we can see with an increasing in the speed, we can see much better safe recovery. So this is the result for reprogramming after printing, that is done separately as a part of post process. So here we can see that with increasing in the speed, the trend is same, that is the safe recovery is increasing. With an increase in the extruded temperature, there is a decrement in the recovery, and safe fixation ratio is good for both of that. But the difference between the two is that for the reprogramming, we are getting only 50% recovery, but for programming during printing, that is the beauty of the FDM 3D printing process, is that it generally programs during the process only. So for that, we are getting more than 87 to 88% of recovery. So these are some of the working prototype that I would like to show, so that we can know what is the future applications of this kind of technology. So here we have printed a wood pile structure scaffold, which we can provide a stress so that it will deform, and when heated it can recover. So these scaffolds are generally used for bone tissue engineering for a replacement for the bone. So here by using this process, we can have a minimal invasive scaffold deployment, so that after the deployment is done, we can provide some external heating from IR sources, or we can also use the body heat to recover back to this position. So we can have a minimal invasive scaffold deployment. Here we have printed the origami cubes with a different process parameter, like for low speed and high speed. For low speed, we can see that it took around 13 seconds to recover, and the recovery is not also fully recovered. So, but for the high speed, we can see that it took only 2 seconds, and the recovery was also completed. So here from this, we can conclude that we can control the safe morphing behavior of the 4D printed part using the design as well as the processing parameters. So at the conclusion, I would like to say that the embedding of the active component during the additive manufacturing can provide a 4D printed part which can be used for creating shape changing components. And the design for 4D printing can be utilized for controlling the self-morphing behavior also. And we can also see that the experimental validation that we have done for the programming during printing and programming after printing has shown a better result for programming during printing, which is the motivation to use low-cost FDM 3D printing technology to and develop new materials for 4D printing applications. So at the end, I would like to conclude by saying that these prototypes may seem simple, but the promises are way beyond our imagination. Thank you.